Hello and welcome to a tutorial on robust Kalman filtering. Like many conferences this year, MFI 2020 is fully online, so we also do this tutorial fully online. There are two parts to this tutorial. The first is this asynchronous part that you're listening to now, which you should listen to before the first conference day, before September 14th. On September 14th, we can take all of your questions and do some more exercises. While we would have very much loved to see you in Karlsruhe, we hope that this online mode also provides you some additional value because you can revisit all parts again and again until you feel comfortable with them. Then I wish you much fun with this tutorial. So let's first briefly get to who we are. You're currently listening to Florian Pfaff, that's me. I'm at Karlsruhe Institute of Technology, and if you were visiting KIT, you can find me in building 5020 in room 130. I put my phone number here, so if you need to call me, that's this number, and feel free to write emails about this tutorial to this email address. I'm already a couple of years in academia, so I've did my undergraduate studies until 2013 at KIT, then become a research assistant from 2014 to 2018 at Intelligent Sensor Actuator Systems Laboratory at KIT, and I'm now a postdoctoral researcher at the same lab at KIT. I'm holding this tutorial together with Benjamin Noack, we can see here. He's also at KIT at the same lab, and I also gave his contact info because you're also able to contact him in this regard. So he's even more senior. He defended his PhD thesis at 2013. Since then, he's a postdoctoral researcher and group leader at Intelligent Sensor Actuator Systems Laboratory at Karlsruhe Institute of Technology, and he has become an Akademischer Rat, which is a special position in Germany since 2017. So where are we located geographically? Actually, we're located precisely where MFI 2020 was scheduled to be held, and that is in Karlsruhe, Germany, in Europe. And we zoom in a bit to see this more precisely. Here's Karlsruhe, it's very close to the border to France, and you can also relatively quickly get to Switzerland, which is here, and also to Luxembourg. Here you can see, for example, Hamburg, Berlin, Munich. So from these three very popular cities, we're very close, relatively close to Munich, and we're also pretty close to Frankfurt, which is here. So it's easily reachable via airplane. We have different research topics at the Intelligent Sensor Actuator Systems Laboratory, but it all revolves around the central topic of systems and estimation. We've got subtopics such as telepresence, this is visual reality related things. We've got distributed estimation, which will also be a bit of a topic in this tutorial. We've got stochastic control here, and tracking, and with tracking we mean a wide variety of different challenges there. So for tracking, we have circular state estimation and estimation on periodic manifolds. That's also something that I'm really interested in. That's one of my research topics. We've got tracking of extended objects. We've got multi-object tracking. We've got multilateration as one of our topics. In the area of stochastic control, we have system identification, model predictive control, MPC, control over networks, which goes along with NCS, network control systems. We're dealing with multi-agent systems. And regarding telepresence, we had projects regarding teleoperative surgery on the beating heart, which was to simulate a still standing heart and compensate its motion so a surgeon can have the impression that he's working on a heart that's standing still. We've got cyber-physical systems, so you merge virtual reality and real phenomena, and we're working with even with real teleoperators and avatars, and we've got, I would say, one of the most impressive haptic guidance interfaces in the world. So what we're dealing with in this topic is we have it in this distributed estimation too. It's not really just limited to distributed estimation. In distributed estimation, we have reconstruction of distributed phenomena. We're dealing with, especially with sensor actuator networks. So if there are multiple sensors and actuators, particularly then you have distributed estimation. Bounds and unknown correlations. Unknown correlations really often arrive in sensor networks. And finally, what's really important to distributed estimation is stochastic and set membership state estimation, which we will deal with here, but we will deal it very generally in the tracking context. The methods that we provide in this tutorial can be applied to arbitrary state estimation problems. State estimation problems include, for example, the very popular application of tracking, so self-localization, estimating the state of some physical phenomena, and hazard monitoring. This really goes into the distributed part where you have multiple sensors and you want to really reconstruct a phenomena, for example, some hazard that is spreading and you want to distribute an estimated spread just using some sensor measurements there. Throughout this tutorial, we will need system and sensor models. Here we illustrate a linear model. In this case, our state, it's underlined because it's a vector, at time step k plus 1 is the system matrix multiplied by the current state k at time step k plus the input matrix multiplied with the input. I put a hat over it to denote that this is a truly known value because we know what we give the system as an input. Then our sensor model. Here we illustrate a linear sensor model. Here that's the observation. We know that for certain. It may be noisy as we'll get to in a minute, but that's related to the measurement matrix multiplied with the state if it's a linear model. How can we model uncertainties? The easiest way is to say that everything is deterministic, but usually it's not the case. So we simply ignore the uncertainties. That's the easiest way, but it will still yield a proper solution in many cases. For example, if you do least squares with just the number of measurements that you need to solve your equation, then you will get something out. So you will not know how certain you are, and you will not be able to properly improve it without being aware of that your measurements, for example, may not be perfect. Then there's a stochastic model. To really work with that based on Bayes formula and everything that you know from Bayesian estimation, you have to know some error distribution. And for Bayesian estimation, you need a prior. As we'll see throughout this talk, with our stochastic and set membership modeling, we alleviate these needs. We can have less knowledge about the error distributions, and we do not need one specific prior. So let's get to how these process models, these system models look like. If you have a deterministic model, you just have this. You have this x is just a times x plus b times u hat And that's all you assume about it. If you say there are stochastic uncertainties, you further add a random noise term in there that you consider in your filter. If you also include set membership errors, there's another error term. But for this, you do not know the distribution. You just know it's somewhere in this region, and you cannot specify any probabilities for that. Matters are similar for the sensor models. If you say that you've got a deterministic model, it's just C is H times X, that's it. If you also integrate stochastic errors, in this case additively, then you have some random noise of which we know the distribution. But then you can also have some set membership errors. Again, you do not know the distribution of that. You just know it lies somewhere in between. So we require less knowledge if we also consider this type of errors. Using the framework of combined stochastic and set membership state estimation will solve two key challenges in Bayesian estimation. And we'll first address two issues: that what is a prior density, how to obtain one, and how can this be improved using sets of densities, and how to obtain a likelihood in real-world settings, which usually include discretization errors.